here consider so-called Newton's methods for finding a zero value of a function. The formula for the Newton method is written here. We have some initial point x0, and using x0 we can find x1, x2, x3 and so on according to this formula. This method is very powerful. The convergence of the method, of the sequence of these points to the real solution is very fast. The theoretical statements that estimates the rate of convergence is presented here on this slide. But the main drawback of this method is that we must know the derivative of a function. As you see, this formula, it includes the function value f of x and the derivative of a function f prime x. But sometimes this method is applied for the problems where the function is so-called a black box, just an algorithm, some function in terms of in programming that has some input and output, and we don't know the formula and we cannot compute the derivative. In this case, when we cannot compute a derivative, we cannot apply this method. So we can apply this method only in the case when we know the derivative, when we can find the derivative of the function analytically. And the first method that we considered is the bisection method. And bisection method doesn't require derivative. It requires only function value. And we just compare the signs of a function at left and right point. But this method, Newton method, is much faster than the bisection method in terms of the error that we obtain after n step of the method. Well, and the geometric interpretation of the method is presented here. We discussed about it on previous lesson in details. That if we know the value of the function at some point xn, and if we know the derivative of the function, then the value of the derivative at this point is the slope of the tangent line. And we can draw this line at the point xn, and we can take the point of intersection between the tangent line and x as the next point, x plus 1. After that, we take this point, compute the value of the function, compute the value of the derivative of this function, draw the next tangent line, and so on. Well, I just review what we discussed about on previous lesson. Okay. 9 students connect to our meeting. Very good. And now let's consider one more method, the final method for finding the roots of the function, the roots of the nonlinear equation, so-called fixed point iteration method. Again, I can say that the idea of a fixed point iteration method is very powerful, and this idea can be applied for solving not only this type of problems, but some other types of problems. Well, let's consider the definition. What is a fixed point? Suppose that we have a function g of x, and a number p is called a fixed point for a given function if g of p equals to p. Well, the definition of a fixed point is very simple. We have a function, and p is called a fixed point when g of p equals to p. Very simple question for you. What is a fixed point for the function x squared? What will be the fixed points for the function x squared? According to this definition, that the g of p equals to p, or I can write g of x equals to x. G of x equals to x. In this case, the point x is called a fixed point. What is the fixed point for x squared?
X squared, the same.
The same? No. You should tell me the value of x, for which the value of a function equals to x. This is a function, the general function, g of x. In this case, in this example, the function is x squared. What is the fixed point for this function? What is the fixed point for which x this is true? Do you understand my question or not? X squared equals to x. Is it true? but not for all the points. For what point this equality will be true?
Assuming that
For what x? For what x this is true?
1.
1. Excellent. 1 is a fixed point for the function x squared, because 1 in square equals to 1. If I consider 2, will it be the fixed point? 2?
No.
No, because 4 doesn't equal to it. Can you say what is one more fixed point, not only 1 for x squared? Another fixed point for x squared is also very simple. 0. 0 in square equals to 0. 0 is another fixed point for x squared. Some functions doesn't have a fixed points. But for x squared we have these fixed points. And the problem of root finding and a fixed point problems are equivalent class of problems. Suppose that we have a root finding problem. Suppose that we have an equation f of x equals to 0. Then we can define a function g of x that equals to x minus f of x, and the fixed point of a function g of x will be the root point for the function f of x. Again, I repeat it, that suppose we want to solve a problem, we want to find the root of the equation f of x equals to 0. We can reformulate this problem and we can try to find a fixed point for the function g of x, where g of x equals to x minus f of x. And if the function g of x has a fixed point at some point p, then the function f of x has a root, has a 0 at p. So these two classes of problems are equivalent. And this is an example of a fixed point. On this picture, we see the graph of the function x squared minus 2, and this function has two fixed points. First fixed point 2, p1 equals 2, and the second fixed point is p2 equals to minus 1. And the graphical interpretation of fixed points is points of intersection between the graph of the function and the line y equals to x. So this is a graph of the function x squared minus 2 parabola. This is line y equals to x, and the points of intersection between these two graphs will be the fixed points for the function y of x. Let's consider one more example that is written here. Suppose that y of x equals to x squared plus 2. What can you say about fixed points? Y of x equals to x squared plus 2. Following this graphical interpretation, what can you say about the fixed points of this function?
Minus 1.
Where is your pen and paper? Draw the graph of the function, and after that, you can answer the question, where are the fixed points of the function x squared plus 2? This graph, this picture corresponds to the function x squared minus 2. This is x squared minus 2. And the fixed points are the points of intersection between the graph of the function and y equals to x. And let's consider another case, x squared plus 2. X squared plus 2. What will be the graph of this function? X squared plus 2. Please draw it, it's very simple. X squared plus 2. This is a graph of x squared minus 2. What can you say about x squared plus 2? Maybe some students who are online already draw the graph and can share the screen and show me your picture with your graph. This is x squared minus 2. How to draw the graph of the function? You draw x squared. This is x squared. This is x squared minus 2.
So plus 2.
Plus 2, right. X squared plus 2. And the question is the points of intersection between x squared plus 2 and the line y equals to x.
Why you put it? It will not touch.
What?
It will not touch.
Right, right. No points. Draw the graph of y equals to x squared. How this? Just x squared. To understand how to write to this one, first you should write x squared. How to write x squared? The graph of the function. third course, Computing Mathematics. X squared. Zero, 1, 1, minus 1, 1. This is x squared. This is x squared minus 2. Minus 2. We move this graph on minus 2. How to write x squared plus 2? We should move it up. We should move this graph up. And when you move it up, you will see that it will be no points of intersection between this graph if you move it up. This is 2 if you move it up. And this line is there. No points. No points. It means that there are no points. No fixed points for the function x squared plus 2. No fixed points. So some function can have a fixed point, but this is a very simple example of a function that doesn't have a fixed point. Well, and on this example again, let me explain the connection between a root finding problem and a fixed point problem. Let's consider again the first function, y of x equals to x squared minus 2. Let's consider again the first the first problem. Y of x equals to x squared minus 2. Okay. And x squared minus 2. There are two fixed points, P1, 2 and minus 1. So when you substitute 2, you have 2. When you substitute minus 1, you will get minus 1. Well, so when I write the problem, f of x equals to x squared minus 2 and minus x, the fixed points for y of x will be the same as the root points for f of x. the fixed points for y of x will be the same as the root points of f of x. F of x is written as y of x minus x, something like this. You can simply check. Even I can type it for all the students that this function. This function is written in the form y of x minus x. It's y of x minus x. Please substitute here 2. X equals 2. 0. X equals minus 1. Also 0. So when you consider the 0 value problem for f of x, it will be the fixed point problem for y of x. So these problems are related. Just subtract minus x, or just add plus x, and you can convert one problem to another. Well, this is the main point, the main relation between root finding problem and the fixed point problem. Is it clear that these two problems are related?
Why you add minus? Why?
Just because I told you, subtract x. This is a rule how to convert the fixed point problem to the root finding problem, and how to convert root finding problem to the fixed point problem. Just plus x. You should take f of x plus x. If you consider some problem of a root finding, f of x equals to 0, you can write f of x plus x, and you get the fixed point problem. Well, I think you more or less understand that the root finding problem and the fixed point problem are related. And also, I show you two simple examples that one function has fixed points, another function, very simple function, doesn't have a fixed point. But what function has a fixed point and what function doesn't have? This theorem formulates the sufficient conditions for existence and uniqueness of a fixed point. Theorem that gives sufficient conditions for existence and uniqueness of a fixed point. I just formulate and try to explain the meaning of this theorem without proof. Here is the proof of this theorem. I think we can skip it. I just try to explain the meaning of this theorem. And you can also, I ask you to make some notes about it, because it's not all information is written on the slide. Of course, all the information you can take from the books that I send you. Well, statement number A of this theorem. Suppose that the function g belongs to the class of continuous functions. This notation g is in C at AB means that the function g is continuous. What is the meaning of continuous function? We discuss about it on the first lesson. So suppose that the function g is continuous. And also suppose that the values of a function g of x are between some values a and b for all x between a and b. Then g of x has a fixed point in some point P between A and B. Well, I try to explain. For all x between A and B, so this is A, this is B, this is x, x is between A and B. We consider the interval from A to B. Then g of x is also between A and B. It means that I can imagine a square and x is from A to B, and the value of a function is also somewhere inside this square. So this condition, these two conditions means that the value of the function is in square, not outside of the square. So the function cannot pass something somewhere here, is inside this square. And the function is continuous. So it means that there is no jumps, no gaps in the function. So the function can looks like this. For example, g of x. The values of g of x are between a and b, and this function is continuous. So it means, yes, and this theorem tells us that the function g of x has a fixed point. We already consider that the geometric interpretation of a fixed point is a point of intersection between the line y equals to x and the graph of the function. So yes, it seems that if the function is inside this box, is inside this square, it will be a point of intersection between their function and the line y equals to x. And the statement B, or yeah, before we consider this statement B, let me briefly draw a small picture that suppose that this is this square, this is y equals to x, a and b, but the function can look like parabola here, something like this, right? Inside this box. And in this point, in this case, it can have 2 points of intersection with y equals to x on this picture on the slide, only one point of intersection. And here I give you a very simple example where can be 2 points. Well, if in addition the derivative of the function exists and the module of this derivative is smaller than k, where k is smaller than 1, for all x between a and b, then the fixed point is unique. Again, the statement number A tells us that it must be a fixed point, but it may be 2, 3, nobody knows how many fixed points. But if in addition the derivative of the function smaller than 1, then this fixed point is unique. Only one fixed point. Because on this example, the derivative will be greater than 1. Greater than 1. If the derivative is smaller than 1, that only one fixed point. Well, I skip this theorem. Well, let's consider this example. Let's consider this example, and let's try to answer the question. Does the function g of x equals to x squared minus 1 over 2 have a unique fixed point in the interval from minus 1 to 1? We should check the statements of the theorem. We should check the statements. The first statement. If x is between a and b, then the function values also must be between a and b. Here we have a and b minus 1 and 1. X is from minus 1 to 1. What can you say about the function values when x is from minus 1 to 1, when x changed from minus 1 to 1, the value of the function will also change from, no, not minus 1, but from 0. Or from minus 1 over 2, right? From minus 1 over 2 to 1. When you substitute x equals to 0, so it will be a parabola, yes? When x equals to 0, g of x equals to minus 1 over 2. When x equals to 1 or minus 1, you get 0, right? When you substitute 1 or minus 1. So the range of the function is from minus 1 over 2 to 0. So it's also between minus 1 and 1. So this is the first statement, and the second statement of the theorem. We should find the derivative and we should check, is it smaller than 1 or greater than 1? No, if it's smaller than one fixed point. If not, it can be many fixed points. Well, what is the derivative of this function? G of x equals to x squared minus 1 over 2. What will be the derivative? Find the derivative of this function. What is the derivative of the function x squared minus 1 over 2? We have the rules of differentiation. This function is very simple. You can find the derivative, the exact value of the derivative.
X.
Right?
X.
Just x.
Yeah.
Just x. The derivative of this function is just x. And when x is from minus 1 to 1, g prime x is also from minus 1 to 1. So it's smaller than 1. The statements of the theorem is true. So this function has a one fixed point. Well, it's just an example how we can apply this theorem. And now let's consider the main idea of a fixed point iteration method. The question is how to find a fixed point of a function. We have a function g of x, and we are going to find a fixed point. So such point that g of p equals to p. Suppose that we have initial approximation, some point p0. Suppose that we have initial approximation p0, and suppose that we generate a sequence Pn by the following very simple rule, that the next point Pn equals to g of p n minus 1. And if the sequence converges to p, then this point p is a fixed point. And this technique is called fixed point iteration method. Again, I just write the main points from this slide on the board. So suppose that we have a function g of x suppose that we have a function g of x. We select the point p0, initial point. You remember that in Newton method we also select an initial point to initialize the process. We select the first point, and after that we apply the rule next, exactly the same. We select the first point, and after that the rule of generating the next point is very simple. Pn equals to g of p n minus 1. We just substitute p0 here and get the next point.
And we are out to
After that, we use P1, get P2, and so on.
Select the
Initial
initial point.
point, so, we should guess. We should, like in previous, like in my previous example, when we find the root of, for example, 17. What is the root of 17? We can guess that the root of 17 must be a little bit greater than 4. So we can select 4 as initial point. And here we also should have some good initial guess for the first point. And after that, this very simple process and converge to the fixed point. Also, as you see, this method is very simple. And this method also sometimes called simple iteration method, not fixed point. Fixed point iteration means that we find a fixed point, but also sometimes it's called simple iteration method. And before we consider some examples, I want to show you the geometric interpretation of the method. Suppose that this graph is g of x. This line is y equals to x. Again, the point of intersection between these two lines is a fixed point. This is a fixed point. We don't know it. We know that it's somewhere intersects, but we don't know the exact value of this point. We select P0 as initial value. We compute the value g of x, and after that we take this value as argument and compute the next value, the next, next, and so on. And this method, this process converges to this point. This is the first point, second point, third point, and so on. So P1 is g of P0, P2 is g of P1, P3 is g of P2, P4 is g of P3, and so on. This is another example of the method behavior. This is a graph of the function y equals to g of x. This line is y equals to x. This is a point of intersection. This is a fixed point. And we are going to find this fixed point. Suppose that P0 is our initial guess. You see that it's rather far from this fixed point. It's our initial guess. We compute P1 as g of P0. After that, we compute P2 as g of P1. After that, we compute P3 as g of P2, P4 as g of P3, and so on. So the process of root finding here looks like stairs. Upper, 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 and this process converges to this point, to the fixed point. And here, like spiral, we start from P0, here, this, and converge to this point. I think I think that it will be good to carry out some few steps of the method manually to understand how it works. To understand how it works. Okay, I showed you this picture. Well, let's consider the following problem. Cosine x minus x equals to 0. Let's consider the root finding problem. Cos x minus x equals to 0. So f of x equals to cos x minus x equals to 0. According to these our consideration here, how to reformulate this problem into fixed point problem. This is a root finding problem. Here we are going to find some point x star for which f of x star equals to 0. It's a root finding problem. What should we do to convert this problem into fixed point problem?
You should add x.
Plus x, add x. So let's introduce another function. G of x equals to f of x plus x, and in this case it's very simple. Cos x. So g of x equals to cosine x. G of x equals to cos x. And in our case, g of x equals to cosine x, and we are going to find a fixed point for the function cosine x, for function cos x. And the fixed point for this function will be the 0 point for this function. When we solve this problem, we simultaneously solve this one. Okay? What point we can take as initial point? Initial guess.
P1.
0.
1 or 0. It's two very simple points for cosine, right? Let's take 0. So let's take the first point. P0 equals to 0. P0 equals to 0. What will be P1?
1.
1?
0.
It's 0
P1.
to 1. It cannot be 1.
How to compute P1? It's written
G is 0.
G of
Equal 1.
P1, right?
Cosine 0.
Right. So the first step, P0 equals to 0. Second step, P1 equals to G of P0. In our case, it's a cosine. Cosine 0 equals to 1. No. No. Why 0? No. How to P2 equals to cosine cos 1. Please use your calculators to compute cos 1. But remember that all the computations with trigonometric functions you should perform in radians, not degrees. Radians. If you use calculator, switch your calculator in radians, because usually calculators by default use degrees. Run calc, also calculator. It's not running. Some problems with computer. It doesn't.
Is it 0.5 or
0 point something.
It's a very bad answer, 0 point something. Oh, it's very bad because computer is not answer. Computer is not answer, and I don't know. I don't know about our meeting. It doesn't help. Control Alt. I can fix it without your help. Yeah. Okay, let's. I don't know. Maybe I can just. Of course, I can restart the computer, but our meeting will be interrupted, and I don't know about other students. Do they hear us or not during the lessons? Because maybe they. Or presentation is working. It's working. Well, somebody hear me or not?
Yes, sir.
Yes, or okay.
Yes, sir.
Because I think that some problems with computer. Okay, if you hear me, it's okay. Do you see the presentation?
Yes, sir. See.
Yes, okay. Well, what is the cosine 1? What?
0.999. Now we convert to
It's 999. It's when you use 1 as degree. You should use it in radians. It
radians. It's
0 point
0.
maybe 0.005. Zero.
0.54.
0.54. Yes. 0.54 and something. After that, we use this point to calculate P3. P3 equals to cosine 0.54, and we get P3. We get P3 in and so on, and so on. When we should stop? When we should stop the process? When we should stop? For example, we should stop it when there P n minus P n minus 1 smaller than given number. Smaller becomes smaller than given number. Well, I cannot close this window. I don't know why. Let me restart the computer, and after that I connect to the meeting. I just restart.
Okay, sir.
I restart the computer.
Okay, sir.
Is that working fine? This one, two, four.
Well, I restart the computer. Now I show the presentation again. Unfortunately, I don't know what will be with the record of this meeting. I hope that it's okay and I can send you the record of this meeting, but I'll check it after the lesson. Well, on this slide you may see the pseudocode of the algorithm, and this algorithm is very simple. This is the main loop of the algorithm. While I smaller than n, where n is the number of iterations. Oh, sorry, I don't share the presentation. Even I share all of the screen because I want to show you also the Visual Studio. While I smaller than n and the distance, the difference from p to p0 is greater than tolerance, then just two main steps. We update the value of p0 and we compute new value of p. These two operations. Of course, on the board I can write p1, p2, p3, and so on, the sequence of the values. But you see that actually we should know only two of them, current and next. The current value is p0, the next value is p. And while the distance between these 2 points are greater than predefined tolerance, we repeat this method. Let me show you the implementation of this method in Visual Studio. Oh, it's no Visual Studio here. Okay, I show you this just as a code. I show you the code. How to increase the font. No, it's not. Let's consider this function that we already consider on the board, x minus cosine x, and this while, oh sorry, so it's a bisection method, it's not a fixed point. Where is fixed point? Fixed point is here, of course. Okay. This is a function. The function g of x. In our example, g of x equals to cosine x. That corresponds to the problem x minus cosine x equals to 0. And this simple loop corresponds to the fixed point iteration method. While FAP's absolute value of the difference P0 minus P greater than tolerance, and the number of iterations smaller than n, we repeat these two simple steps. We update the value of P0 and we update the value of P. P0 equals to P and P equals to G of P0. And we increase the counter. If the number of iterations equals to n, it means that the method failed to solve the problem after n iterations. Otherwise, we should output their solution to this problem. Well, here we see the code. The code is very simple, just 3 lines. Okay, some theorems about their convergence, I think we can skip it. Well, questions about fixed point iteration method. I show you the program that implements the fixed point. Try to reproduce it. Try to implement this method on your computers and try to solve this problem with the functions cosine x minus x equals to 0 and cos x as a root finding problem and cos x as a fixed point finding problem. Well, let me repeat that next week it will be no lessons because I will be on a conference. But week after week we will have 2 lessons from 9. I will send you email about it before the lessons. Well, that's all for today. Let's finish our lessons. I will send you the I'll check the okay, I'll check about the video file. Because I don't know what happens. I hope that it will be okay, and later I will send you the video record of this lesson. That's all. Goodbye. See you on April 5.
Thank you, sir.
Goodbye.
See you, sir.
Goodbye.